Welcome to the next tutorial on RP1 with Principia. And some people asked to do a tutorial about antennas, orbital comm networks. I want to split those tutorials into two parts. So this will be the first part, focusing on the antennas, selecting the technology, why and how that works, and and how to choose your orbital vessels, your deep space probes in regards to the COM technology, and what would be the most beneficial selection there. So disclaimer as always, so this tutorial or guide is rather for beginners, so there's no, there might be better stuff out there that you can find that will go more in depth, because I will not be using, at least for this tutorial, any math at all. Basic understanding of physics should be there, because we'll talk a little bit of physics, how antennas work, but I don't want to get into math. I don't want to pull out the formulas to calculate the gain, the bandwidth. You can look that up if you want. There are better tutorials out there, especially from academic sources. So I'll leave that to it. Um, so for the considerations of selecting the proper antenna, configuring the proper antenna, um, we usually have three properties that we need to satisfy. So the first one is distance. So how far do we want to communicate with? Do we need bandwidth? So is that just for command and control? So we just need little bandwidth just to get basic functions, control the probe, for example. Or do we need actually good bandwidth because we are transmitting science data, video data, lots of megabytes, and we need to do that in due time. And also power supply, because antennas, comm systems, contacts can draw a lot of power if configured wrongly, and this will make your probes bigger and not even have a proper electrical economy working on the probe, so it might drain the batteries even though it's fully lit on the solar panels. So having that in the back of your head, we can go down and see how and where to select those antennas. First consideration also is the options, the ComNet options that I usually play with. So the modifiers will be 1.0. Got the extra ground stations enabled, but also requires signal for control and plasma blackout. Especially the first one is, in my opinion, pretty important, because you wouldn't need antennas or that much if you play without that option enabled, because then you can, especially when it comes to an orbital comm relay, there's no need for that anymore, because you can just, control your rocket. It's only there then for transmitting science, but that's another thing we will take a look at. When does it start to get important? So let's say you're doing a normal playthrough. It starts to get important, in my opinion, when the early moon contracts come up. So what do we need to achieve with those contracts? So we need to get something to the moon. That's, at least in my playthroughs lately, it is the first time you actually need advanced orbital maneuvers where you actually coast in a parking orbit and then have to execute your maneuver on time. You need to get some data back from the moon to achieve those contracts, to successfully um, finish those contracts. And of course, you don't you can't run out of juice on your probes. If they go electrically dry, you can't send data back, and the contracts will fail too. So you need proper energy management. Um, Starting out, we probably have researched the first Luna ComTech a node there to actually get the technology and data to have a sensible probe that is able to communicate with us on Earth, back on Earth. And the question then is, also, after those moon contracts, why do I need an orbital comm relay or a relay network? It's pretty simple. So my best drawing, I tried my best drawing skills. So you're on low parking orbit with like 150 kilometers, for example, and you have a ground station. And due to the Earth curvature, I know it isn't flat, but yeah, since it isn't flat, you can't reach it. I mean, there's some geometry here, so you can see that you can't actually see the ground station, so you can't communicate with it. How do you fix it? You have a satellite that's way higher up, usually like 20, 30K up, that is able to actually see the ground station and to see you, and then communicate with you. You communicate, or your space probe will communicate with that relay, and that relay will get back to ground station. So you have a reliable data connection. Things to consider here is the bandwidth and the power you need to have communication over the distance. Also, the frequency band has to match with the antenna you have here on that space probe, and then you can actually make it. For this, in the back of my head, I think you need at least to have the the digital communication node research. I think that's tier 2 or tier 3, but it will say so in the tooltip. So how do I do this? How do I do the early moon contracts in regards to communication? Um, we have to decide on a few factors. So we have to decide on the frequency bands, on the antenna used, and the tech level. So the question is the highest tech level always the best approach? The bigger the antenna, is it better? Um, and the only answer I can give you here is, well, yes, but actually no. Of course, a bigger antenna will have can support better codecs. It has more gain, um, and it will have usually then a higher bandwidth. But do we actually need that? And I'm going to argue no. Let's just quickly switch to the game so we can actually do some fun stuff here. So I got a probe core here, and let's just imagine that we want to run this as um, a com relay. So it has to see the ground station, it has to see you. And so, for example, we're going to get this big antenna up here, put it up here, say, well, yeah, that's a lot of gain, we can use that. So let's go into the antenna planning. And we can see we have the S-band, for example, X-band. Let's take the higher bands and go into antenna planning, or just look at the info of the antenna itself. Let's go here. And I don't know if you can read this, but there is also a property that says beam width. So let's say you take the Ka band, where you actually have the highest gain, um, but it only has like 0.4 degrees of beam width. That means the beam itself is more or less like a laser. So if that focuses your ground stations, it will probably not even see or it reach your craft. So the relay network won't work because it can only communicate to one craft at once. So you would probably go down, in this case, back to the VHF antenna, but you can also see it's only 87.1 of beam width. So in an orbital common relay network, it is enough, that 90 degrees angle, usually. Um, but the question here is that the weight of that thing is about 20 kilograms. Um, you can do it a little bit easier. For example, with the first relay antenna you get, the Communitron 16. Um, Taking this antenna, you can see it's an omnidirectional antenna. It has less gain, but for an orbital common network, we don't need bandwidth. Like it is enough to just have that little bandwidth enough to actually command and control your rocket that you have in low orbit. So taking this, and we can see we have tech level 10. The power it is taking right now in idle configuration is 9.5 watts. And if we dial it down to tech level like 2, it's only 8. And then it's going up like tech level 3, it's almost 20 watts, 25 watts, 23, and then it's going back down. So I think you need at least to have tech level 3, tech level 2 for the COM network to work. I have to double check that if once you've researched it, if you can also go for tech level 1 and have that work as a COM relay bit, because then your power is only 0.3 watts, and then you hardly take any power, and this is way better to keep this up um, as an orbital rocket because you don't need as much solar panels. It can be lighter. You need less battery. So yeah, but let's just consider we're taking tech level 2. The question is now, what about the bands? So this is only VHF and UHF bands available. So which band do we take? And for this, we usually go into antenna planning because the beam width is the same. That thing is omnidirectional. So let's go into antenna planning. And in here, we can see that that we have two antennas on the vessel, the internal antenna and the one on the outside, and we have the ground stations we want to communicate to. So we get the best station here with a big gain, but let's say we can't see that station. So we take the worst station we have that we can visibly see. So that's like the 40 decibel one in UHF. We click on that, then we click on the antenna that we have on the spacecraft that we want to use and calculate with, and also the ground station tech level. So right now it's 10 because I'm in a sandbox tutorial here for you, but let's dial that down to 2 as well. Apply this real quick. So we take this as a UHF band, 40 decibel, and then we take this one. So now we have to consider the distances. Let's say we're like almost in a geostationary orbit. So that's like what, 36,000 kilometers, plus minus, let's say a little bit more, 45,000 here. So we can make sure that works. And then we click on plan and we can see there's no connection happening. So right now on the UHF band, we don't have a receive, a transmit or receive connection. Switching the antenna to VHF, you have to select the ground station again because it differs now in the band. And now you can see we actually have a connection. So switching from the UHF band to the VHF band, we took the bandwidth down, so we transmit less data per second, but the range is longer. And this is enough for 30 decibel transmit power on that antenna to actually get a connection in this low geostationary orbits to anything that is flying down in low Earth orbit. So what I would usually do then for those relay networks is I'm going to take a VHF band antenna and I have one on my spacecraft. So usually the spacecraft that I have in low Earth orbit is not the deep space probe I'm flying because that's just a bus that's there to inject me into that orbit. And then I release the probe. So I have two different antennas there. I have one in the VHF band for the lower Earth orbit and another antenna for my spacecraft. The question is, what antenna do I take for that spacecraft now? It will be further away from Earth, so the beam angle doesn't really matter anymore. Then the only thing that really becomes important is the distance and the bandwidth. The question here is, do I need that bandwidth? Like if I'm just transmitting like temperature data or barometric data, I probably don't need that much bandwidth as I would do with other experiments. But let's say we want to keep this as early tech as possible. Um, what antenna do we usually take? So we got probably this one here. That's a little bit early down the road, like in the early 60s. Um, so let's configure this real quick. So it already has the S band. You can go in the higher bands, but you will probably start with the S band. And the difference here is in the S band, you have more than twice as much gain than in the UHF band, but your beam width is down to 11 degrees. That doesn't really matter anymore, though. So once you've started that probe, you disconnected it from your bus, it's going deep space in a very, very short time, probably like a few hours. The whole Earth will fit in that 11 degrees. And so you can actually take this. The question is now, how do I calculate the transmit power? It's quite easy. So it's calculating this from, you have the presets here. So let's say you want to send your first probe to Venus. It will automatically put in the maximum distance that Venus is away from Earth and the minimum distance, say at opposition. And so we take the best station, we take this with the S-band, we take this antenna we've selected, click on plan, and we can see there's no connection. So we probably need to up this to tech level 3. So the ground station is tech level 3. Um, the no, can it be tech level 2? No, it can't. Can it be tech level 3? Not yet. So it won't probably be able to reach. Oh, it's UHF. Of course, we need to take the S-band. Best station here. Let's take the best station. Let's take this. Let's plan this. And now we can see that at maximum distance, there's no connection. Why is there no connection? We can still receive data from Earth, but we can't transmit data from Earth. At the minimum range, we can. So we can roll the dice and probably do mission planning properly and say, what is the maximum distance I will be away in Venus in my mission time frame? Or if you want to play it safe, you can just increase the transmitting power of your antenna. And you can increase it, increase it, increase it. Okay, in this case, it will not be able to. Oh, it will be able. Hold on, it's not updating. So you go back to like 34 decibels, still no connection. You go like 36, nope. 39, nope. 42, nope. 43, yeah, there's a little bit there. But you can also see it's taking a lot of power. It's taking 170 watts if it's transmitting to Earth. And that's the power drain you have transmitting data to Earth from your experiments. And it's quite high, especially for early on. So the question is it really worth it? Do your mission planning. If you can say, well, it's not 250 gigameters, it's only like 200 in the mission time frame, and then you plan it properly again, and you can probably get down a bit here, like 41 decibel, and then reduce that from 170 watts to like 116. That's up to you. You can do the mission planning. And NASA's mission planning tool. You can do it in Principia. We've seen that already in the tutorial on how to get to the moon. The basics of the mission flight and yeah, that will probably help you decide on taking the proper band, proper tech level, and the transmit power. So how to set it up? Usually for orbital relay, I would go with low tech, like 3 or anything way higher because of the power drain. We maybe 2 will work. We'll have to check that, but you get the power drain here. The antenna is an omnidirectional is enough. Directional low tech. And the band, I usually take the VHF band because longer range than UHF, but less bandwidth. It's enough to control your spacecraft. For deep space probes, the tech is as applicable. Select the best tech rate and the power drain. Try to balance it out if you need to, especially later down, if you're like in the 70s. What kind of antenna to choose? Here, I would actually say depending on the weight, of course, you have a weight limit on your missions regarding your delta V, but the bigger the better. Or the better gain, more gain, the better. And then the band, not all antennas support all bands. Also, the best one you can get. We can still take a look here, for example, real quick with the high gain antenna here from the Apollo block. It has like in the Ka band, it has like a 52 decibel of gain, while some other ones have only 44. So that will increase the distance you can use that antenna. I mean, we have this antenna here on here right now. That's the 49er. Let's get the 3-meter antenna up and see the difference here in the antenna planning. Put it on here as well. We can see, so this one is only transmitting in S-band on tech level 3 with the 30 decibel power. We can select it here, here, planet. So it's not working. Let's go to 33. And also with now with 33 decibels, you can already achieve data transfer on that 200 gigameters, and you only have a transmit power of 34 watts. So that antenna is actually better for the communication. But this one is about 7.4 kilogram, while the 3 meter one, and that's way down the road from the technology perspective here, but um, that's like 39 kilograms, so more than 5 times the weight. That's up to you. That's up to your mission planning, how much delta V you have at hand, and what the best antennas is you've got. So in essence, take a look at the beam width, especially when it comes to orbital comm relays, or if you have a lander that you place on Venus, for example, or Mars, or Moon, on the backside of the Moon, it needs to communicate with the orbiting craft, and that orbiting craft needs to relay it back to Earth. Same mechanics apply there. Or yeah, um, the band that is available, the decibels, the power. The first mistakes I've did was just getting an antenna in the planning. Oh yeah, it looks good. Yeah, I get the decibel up to like 42. Put the antenna into orbit of Venus, and then fail communications because it would immediately, like sending data, it would immediately drain the battery. Uh, and that's a mistake you can easily avoid with just um, using this tool here. So you check the electric charge. So right now the electric charge is for 205 days, but you have this active transmission time here. And this is what reflects here. So let's say we're going to transmit now 100% of the time. We can see that the electric charge duration is going down to 160. So in this way you can actually um, uh, calculate, plan it already beforehand, how much power it's going to take, how much power it's going to drain, especially here with the higher gain antenna, with the higher power antenna now. We can see going down here, it's only for 76 days now, if that's completely transmitting. And if we would have went to like 46, but it's only 32 days. So it's really cutting down on the battery, and you can actually work this here with the active transmission time. In case you didn't know what that slider was about, I didn't when I first started out using the real antennas, and it helped me a lot in mission planning. Right, so more or less that's it for now for the tutorial. I know it hasn't been fancy, but I just want to transmit some information here. And in the next step, we will look at how to actually position an orbital comnet with early technology in orbits, and then with intermediate technology, so you can get a proper comm network up early, like in the late 50s, and then maybe a little bit later down the road if you can actually do precise orbital maneuvering. That's it for now. Have a good one. Thank you for listening and tuning in. And if you have any questions, remarks, put that back in the comments, and I'll go back to this. Have a good one.